Good morning, everybody. So, as announced by mail, today's lecture is streamed as well. For those who might be unable to come here due to the public transport strike, how bad is it anyway? No idea. Okay. So last time we spent the lecture discussing stability issues, and we first derived an equivalent of the Jeans wave number that we had already encountered when we spoke about sound waves. We saw that exactly the same formula, when you replace the sound speed squared by the velocity dispersion, applies to self-gravitating systems as well. But of course, we couldn't refrain from shedding doubt on this estimate by seeing that the Jeans wavelength, right, the inverse of the Jeans wave number, is necessarily, due to the Virial theorem, comparable to the size of the system. And that means that in specific stellar dynamical systems, you should apply dedicated stability analysis if you really want to know what is going on. Also, we saw that the phenomenon of Landau damping also applies to wave-like perturbations of self-gravitating systems. Okay, then we went to disks and had a look at, first of all, the Poisson equation in the idealized case of an infinitely thin disk, infinitely thin, I should say, and flat disk. And we saw that in that case, the Fourier transform turns into a Hankel transform in which the cylindrical Bessel functions appear. And then you can express the potential of the disk by the sequence of convolutions with cylindrical Bessel functions, which is difficult numerically. I talked about that. Okay, and finally, we made a stability analysis of wave-like perturbations of thin disks, and saw that disks are globally stable against perturbations if Tumor's criterion is satisfied. And Tumor's criterion essentially says that if the disk is not too massive and if it's rotating fast enough, it's going to be globally stable against perturbations. Do we have questions up to that point? Not the case? All right, then today I would like to discuss maybe one, maybe two very interesting phenomena with which I would like to conclude the lecture. One is the phenomenon of dynamical friction. It's a phenomenon of friction in a system that is perfectly energy conserving. Right? You have energy conservation everywhere, and yet you have a friction phenomenon. You need to see that. And if we have sufficient time left, I will speak about the Fokker-Planck equation. First of all, because it appears frequently. Second, because it's one way of taking collisions in systems into account for which we have so far only used the collisionless Liouville equation. Okay, so far so good. So the material for today's lecture is contained in vastly separate parts of the lecture notes or the book. So first of all, dynamical friction is in section 5.3, and when I went through it, I was thinking, well, all of this can be said so much more simply. And I will do that today, and I will rewrite this section again. The substance will not change. It will just become much more transparent. Okay, and then the part about the Fokker-Planck equation is in section 1.4 here, elementary kinetic theory. If you scroll down to 1.4.3, diffusion in phase space, the Fokker-Planck approximation. So all of that is somewhere, just in separate parts of the lecture notes. All right. So And off we go. Dynamical friction. This will lead to a famous formula that is due to Subramanian Chandrasekhar, which has frequently been reconsidered because of its somewhat idealizing assumptions. But I think the principle is nonetheless worth seeing. So what's the point? You have a perfectly energy conserving system, and we encounter a friction phenomenon. So how the hell, right? The point is this. Suppose you have a distribution of small masses, and then you send a big mass into that, like this. So what will happen? Suppose I'm the big mass, small masses are flying past me. They will be deflected by my presence. Those who are coming from here will be deflected in this way. Those who are coming from here will be deflected in that way. So I will collect a wake behind me, an overdense wake. And this will have a slight surplus gravity compared to the rest and slow me down, at the expense of accelerating those behind me, of course. Right? So it's perfectly energy conserving, and the friction phenomenon means the big mass, me in that case, is being slowed down by moving through this collection of small masses. That's the whole point. Now let's have a look at that. I need to collect a number of things that essentially you should know. And they have to do with the Kepler problem. But let me collect them over here. So first of all, if two masses encounter each other and do not get gravitationally bound, then what kind of orbit do they describe? Hyperbolic, right? Hyperbolic orbits. But who is describing these hyperbolic orbits? We have two bodies. What's going on? This is annoying. I'm afraid I can't help it. Anyway, so hyperbolic orbits, but who is describing this hyperbolic orbit if you have two bodies? Yes? Exactly, very good. Okay, so we have one big thing. That's an object with a mass capital M. We have one small thing, and of course later we have to generalize for many small things. So they have these positions. We have a relative coordinate vector r pointing from large mass to small mass, and the equation of motion for this thing is this here, right? And mu is the reduced mass between capital M and small m, so it's capital M times small m divided by the sum of them. Okay, alpha is the coupling constant, and in case of gravity, that's just TMM. Okay, and mu is this thing, the reduced mass. Okay, now R can be described by the orbital equation that you have seen in the treatment of Kepler's problem. Right? This is a conical section, and R of phi is given by the orbital equation for the conical sections. Right? You have an orbital parameter p, which essentially is calibrates the size of the orbit. You have in the orbital plane an azimuthal angle phi, which is chosen such that phi equals 0 corresponds to the moment of, or to the point of closest approach. And epsilon is the eccentricity of this orbit. And for a hyperbolic orbit, what's the eccentricity? Larger than 1, exactly. So for a bound orbit, it would be smaller than 1. For a parabolic orbit, it would be 1. For a hyperbolic orbit, it's larger than 1. Now, epsilon square is 1 plus 2 energy of the thing on the orbit times its angular momentum squared divided by alpha square mu. Alpha square mu, exactly. You get this from the solution of the Kepler problem. Right? Okay, now for a hyperbolic orbit, since epsilon is larger than 1, you see that the object can escape to infinity. Right? Because the denominator can become 0, and it does become 0 for cosine phi equals minus 1 over epsilon. And I call this phi bar, right? This will be the angle, the azimuthal angle in the orbital plane where our object escapes to infinity. We need that. Let me make a sketch. So that's the x-axis with respect to which I measure the angle phi. Here is the center of gravity. If I have to do with two objects and a two-body problem, what's the blue point? Center of mass, right? So neither of these objects sits in the blue point. Right? Okay, and then we have a hyperbolic orbit of which I show half now with a red line. And of course the other half is symmetric to that. All right, and now we need the angle phi bar. And for that, I'm constructing tangents to the asymptotic branches of the hyperbola. I'm taking parallels to that, running through the blue point. And then this angle here is phi bar. Okay. Now what's the scattering angle? We're going to need the scattering angle, right? It's the angle between the incoming and the outgoing asymptote. So we take the complete angle, 2 phi bar here, and subtract pi. So then you see the scattering angle theta is this here. Right? It's the angle by which the outgoing asymptote deviates from the incoming asymptote. Yes? Because if you take the difference here, it's this angle. Right? So it's pi subtracted from 2 phi bar. Sorry? What exactly is theta right now? So this one would be the continuation of the incoming asymptote. This is the outgoing asymptote. So this here is the scattering angle. So that's 2 phi bar minus pi. Okay. So these are the things that we are going to need. right. Now the rest will be relatively simple. There's one more thing that I should say right away, namely the center of mass, unless external forces are acting on it, will follow a straight line, will follow an inertial path. So the center of mass coordinate capital X, which is small m xm plus capital M x capital M divided by the sum of masses. That's the center of mass coordinate. It has this velocity. And this velocity will not be changed. Okay, that's also an aspect we are going to need. All right. Now essentially, on the left side of the board, we can just collect things. First of all, I'm defining a velocity which is just r dot. And as you see in the sketch over there, r is the vector connecting small m to large m. So this is Vm minus Vm, small first, large second. Okay, that's that. So this means that if I change velocities Vm and V capital M in this way, then the relative velocity of the two will change by this amount, of course. Okay. From the inertial motion of the center of mass, I can conclude that any change in V small m must be related to any change in V large M in the following manner. Oh, sorry. So small m delta V small m plus large M delta V large M must be 0. So from here I can conclude any change in the velocity of capital M. And remember, that's what we want to know. Right? I want to know if I fly through a collection of small things, how is my velocity going to change? So delta V large M, that's our target. This is minus small m divided by large M times delta V small m. But delta V small m is nothing that we will gain from our treatment or our knowledge of Kepler's problem. Kepler's problem will give us delta V and not delta Vm. So I'm substituting for delta V small m, delta V. So this is minus m divided by capital M, delta V plus delta Vm. Okay, now we can collect the changes in delta Vm and solve the corresponding equation to find, this is this prefactor here, minus small m divided by large M, and times large M divided by M plus M. That's what you get if you bring delta Vm times this prefactor to the other side. Then you will have a prefactor of delta V capital M, that is 1 plus small m divided by large M. And then you will have to divide this over and get this term. Okay, capital M cancels. What remains is small m divided by the sum of masses. But this is the reduced mass mu divided by the large mass times delta V. Okay, so in other words, now we know that if we apply the solution of Kepler's problem here, in the case of a hyperbolic relative orbit, then we can translate the velocity change of that fictitious particle that replaces the two-body problem there to a change in velocity of the large mass m, and this is what we want to know. Okay, this is part one, right, or part A. This is just about the kinematics of the whole problem. Okay, now we have to do now, or we have to find by what degree the relative velocity v is changing during one encounter on a hyperbolic orbit. Now, of course, we use results from Kepler's problem. And I say, I know the scattering angle, theta. So if I take the sine of theta divided by 2, then this is the sine of phi bar minus pi over 2. And the sine with a phase shift of 90 degrees is a cosine. The sine with a phase shift of minus 90 degrees is minus cosine. So this is minus cosine phi bar, so this is 1 over epsilon. Okay. Then what is the cosine of phi bar? Then it was this nonsense. What's the cosine of theta over 2? You see the scattering angle is less than pi. So theta over 2 is less than pi over 2. So this is just the square root of 1 minus sine squared theta half squared. Sorry, the square root of 1 minus sine squared theta half. So that is the square root of 1 minus 1 over epsilon squared. So it's square root over epsilon squared minus 1 divided by epsilon. I'm doing this kind of gymnastics because I want to know what is the sine and what is the cosine of theta. Because once I know that, then I can decompose the velocity into perpendicular and longitudinal components. That's what I want to do. So now I'm going to use sine theta is 2, sine theta half, cosine theta half. So this is 2 times square root epsilon square minus 1 divided by epsilon square. And I'm going to use cosine theta is cosine square theta divided by 2 minus sine square theta divided by 2. And this is nice, you see, because if I square the cosine theta halves, I get epsilon square minus 1 divided by epsilon square. So that's 1 minus 1 over epsilon square. That's the cosine square theta halves. And then I need to subtract 1 over epsilon squared. So I just get this. Or this result here. Okay, and what we need for moving on is this and that result. Okay. I need to go to this sketch again, and I'm going to rotate the sketch now such that my hyperbolic orbit looks like that. In other words, I want to rotate it such that it starts with a horizontal asymptote. So now, the previous coordinate system looks like this. And the incoming asymptote is flat. I need this later also, but for the moment I need that in part C already. The perpendicular velocity, V perpendicular. So that would be the velocity component of the outgoing orbit in the direction perpendicular to the incoming direction. Right? This would be minus V times sine theta, the scattering angle. So it's minus 2V over epsilon squared, square root epsilon squared minus 1. And V parallel, that would be V times the cosine of theta. Just this result over there. So it's V over epsilon squared, epsilon squared minus 2. All right. So it has decomposed the velocity of the outgoing object into a component perpendicular and component parallel to the incoming direction. And I want to know by how much has this changed in comparison to earlier. Well, since I relate everything to the direction of the incoming motion, this is V perpendicular after the encounter minus 0, right? Because originally, by definition, the object did not have a perpendicular component. That's how I chose the coordinate system. So this is just V parallel, so this is minus 2V over epsilon squared, square root epsilon squared minus 1. Okay, and the minus sign, of course, reflects that the particle goes down in that sketch over there. Similarly, delta V parallel is the parallel component after the encounter minus the parallel component before the encounter, but the parallel component before the encounter is just V. So you see, from V over epsilon squared minus 2, I have to subtract V. But here the epsilon square cancels, and this means that V goes away, and I retain, that's minus 2V divided by epsilon squared. Okay. But now remember our relations between the change of the velocity V and the change of the velocity of the big thing. Right? So I just need to translate this now, saying that delta Vm perpendicular, this is minus mu divided by capital M times delta V perpendicular, so it's this expression here, 2V mu divided by capital M epsilon squared, square root epsilon squared minus 1. Have a look at it, it's beautiful, we don't need it anymore. Then we have delta V m parallel, that's the one we are going to need. This is minus mu over m times this expression here, times 2v divided by epsilon squared, negative, so plus. So we have v mu divided by m epsilon squared. There should be a negative sign, in fact, because of course the mass capital M is being slowed down. Nonetheless, let's ignore that for the moment. So in the encounter, the mass capital M has its velocity changed by this amount. That's by one encounter. And now, of course, I have to sum over all encounters that it has. Where are you now? Are you on the upper board or the lower board? Here or there? Yes. Suppose phi bar is 0, then this is minus 1, as it has to be. Okay, anyway, so this is the change of the velocity of the capital of the large mass. Now, what do we have to do in order to sum the effect of all encounters First of all, I need to count how many encounters I have, count the number of encounters. And then I will get the complete change of the velocity of m, capital M. I'm now going to ignore the change in the perpendicular direction of that velocity. Why? Because if I have an infinite distribution of small masses, I will have exactly as many encounters from the left as I will have from the right. So the perpendicular components must add up to 0 on average. So let me ignore them right away. Right? So if I now want to know by how much the velocity of capital M is going to change per unit time, I need to take this result here and multiply by the number of encounters per unit time. So I need to multiply this by the area of a ring with radius b, the impact parameter, times the width dB of that ring. This ring will move forward with a velocity v. And I need to multiply with the density with a density of objects which have mass, which have velocity v small m. So this expression here is the number of small masses with velocity vm that I have available, number density of small masses. This number density multiplied with this volume here, volume per unit time, gives me the number of encounters with small objects of velocity vm at impact parameter b. Okay? And I need to insert the relative velocity v of the two. So this is why not v capital M appears, or v small m, but v. It's the relative velocity of both. Okay, and now of course I need to integrate over dB, and I need to integrate over Vm. And then I get the whole beautiful result. All right, let's do that. The only thing that will depend on the impact parameter is the change of velocity delta V capital M parallel. Why? Let me factor out the first part of this integral and say this is the first thing I want to do, right? I want to carry out the B integral. This I need to integrate from impact parameter 0 to somewhere, and I don't know what somewhere is. And it must be the boundary of the object. I don't know where that is. Now, in some way, we need to relate the impact parameter over here to the eccentricity of the orbit. How do we do that? Let me return to the definition of the eccentricity up there. E squared is 1 plus 2 energy angular momentum squared divided by alpha square mu. And let me now use two things. First of all, the energy will be conserved in the encounter, and the angular momentum will be conserved, right? Because our fictitious particle with a reduced mass will move in a central field of force. That's why the angular momentum will be conserved, and the strength of the gravitational field will not change over time. So energy will be conserved as well. Now I'm using that the energy is mu over 2, right? The reduced mass, because we are dealing with the fictitious object with a reduced mass over 2, times the velocity squared. And this is now the velocity far away from the location of the encounter. It's the velocity at minus infinity. This will remain the same, right? At the same time, the angular momentum will be mu bv. Right? Let me sketch that. So I'm now again in the coordinate system where the particle initially has its velocity directed along the x, in parallel to the x-axis. So over here, the velocity is v. The impact parameter is this, right? And so the angular momentum at minus infinity is the projection of the radius vector at minus infinity on the y-axis, which is b. Right, so the angular momentum is mu bv. All right, now let me collect terms. So therefore, epsilon squared is 1 plus 2 over alpha square mu. Now, mu over 2 v squared is mu bv squared. So you see what remains is 1 plus the mu half cancels, and we get mu squared b squared v to the 4th divided by alpha squared. That's the eccentricity of the orbit. And you see, the larger the impact parameter, the more eccentric the orbit has to be. And there's a one-to-one relation between the two. So in other words, I can replace the BdV integral by an epsilon d epsilon integral. All right, so you see from here that d epsilon square equals mu square v to the 4th divided by alpha square times d b squared. That's what I was driving at, right? I need to carry out the impact parameter integral. I now realize this is an integral over eccentricities. And that's much easier. Okay, so 2b db is db squared. So I have pi times an integral over b squared of what? Delta v m parallel 2v mu divided by m epsilon squared. That's this one. And we are done. I need to integrate from 0 to b max. I can write this as 2 pi v mu divided by capital M. Now, d epsilon square divided by epsilon square, right, because d epsilon square is something times db squared. But now I have to take a prefactor into account, and the prefactor is the inverse of that. It's alpha square divided by mu square v to the 4th. Okay, and I need to integrate this now from 1, because if b squared is 0, then the eccentricity is 1. And this goes to epsilon max squared, whatever that is, right? Oh, sorry, then I need to write b max squared here as well. Okay, so this is just a logarithm. And the logarithm of epsilon max squared divided by 1. So if I collect terms, this is 2 pi. One of the mu's cancels. So I have alpha squared divided by mu capital M. 1 over velocity to the 3rd power. ln epsilon max squared. And again, we have an expression containing a logarithm that we don't really know what to do with. That's the Coulomb logarithm that we encountered several times. And this is typically written as ln 1 plus lambda squared, where you see lambda squared takes the role of this expression here, with a maximum impact parameter inserted. So okay, so this is the result of our integration over the impact parameter, and we can't move any further before we specify what lambda really is. But okay. So now let me collect intermediate results. This is now that part of the complete integral that we are driving at, which dealt with the integration over b only. So what remains is now that we need to take this result here, multiply with the relative velocity, multiply with the number density per velocity space element dvm to the third power, and integrate over all velocities. So what we now need to do is, and we do this after the break, is to carry out the following integral. First, I'm pulling all the constants out of the integral up to this point. Now a factor of 1 over v cubed remains, and I have a velocity left that I need to multiply with. Let us not just cancel that, right? Because that's not what is meant. We have to change a vectorial quantity Vm. So now we need to take into account that we have an expression like this, right? Vector V divided by absolute value V cubed. F of Vm d3 Vm, and this we need to carry out. So this is now the final task that we have to do, and this we do after the break. Yes. Okay. This is usually taken out of the integral, and usually the lambda square is taken as a constant, characterizing the whole system. All right. Yeah.
Hi, sorry for the delay. I just want to announce this year's Heidelberg Integration Bee. Nice. The Integration Bee is, as the name suggests, an integration competition among students where you compete against each other to finally reach the final and fight for the title of Grand Integrator of 2025. And the date for this year is the 27th of May, so mark it in your calendar. This competition is really for everyone from bachelor up to PhD candidates, and we will make sure to make the difficulty fit to everyone's needs. Just one short reminder, this competition is in German, but this should not prevent you from joining or applying. I just wanted to mention it. And if you are interested, you can scan this code as a preliminary registration. It is not binding, it's just for us to see who is interested. And even if you are not interested in competing, feel free to come. Last year was a great success, and we will also have a few special guests. So yeah, you can come if you want. Thank you very much.
One preparation for the Integration Bee is going to be what we are now going to carry out. That's in fact very nicely timed. So we need to solve this integral. Let me write this in a slightly different way, because this is now a very general procedure. First of all, I need to convert the relative velocity v to the velocity v small m, because that is what we are going to integrate over and what the distribution f is parameterized by. So we have that. And let me assume, for example, for a Maxwellian distribution, that the distribution function f as a function of Vm is a function of the absolute value of Vm, not of its direction. Okay. So we have to do with an integral of the sort and of course, by renaming the variables, nothing changes. But just want to show that this is a very general approach now. Can write this expression as a gradient. Namely, in that way. Right? The vector divided by its absolute value cubed is the gradient of 1 divided by the absolute value of x minus y. Okay. If I exchange x for y, just the sign changes if I take the gradient, right? So I can write minus f of x integral over this expression here. Now the gradient with respect to y of this, right? But now I'm integrating over a different variable, then I take the gradient, so I can pull the gradient out front. Now the result looks like this. But I can grossly simplify that. So if f is in fact a function of the absolute value of x and not of its direction, then I can write this as x squared dx d mu d phi, where mu is the usual direction cosine. The phi integral, well, yeah, also I can use here that the absolute value of x minus y is the square root of x squared plus y squared minus 2 times xy mu, the direction cosine, right? I keep the direction of y fixed. I rotate y into the z-axis of my coordinate system. And then I have to integrate over mu. I can simply integrate over phi first, right? It gives me a factor of 2 pi because the integrand now doesn't depend on phi anymore. Then I can carry out the integral over mu, which gives a very simple result. And then I can integrate this further. All right. Let me write down the result. And of course, during the integration B, you can carry this out. So this is going to be this expression here. How do you do that? Well, you find details in the lecture notes, but if you first take this integrand here, insert this expression here, and carry out the mu integral, you see the integral is of type integral d mu over square root a plus b mu. And that depends on the ratio of the two constants a and b, right? Or on the ratio of 2xy and x squared plus y squared. And this is how the separation of the integral here appears. First, you have an integral over x from 0 to y, and then from y to infinity. So this is a general result here. Now we need to apply the gradient with respect to y. And I do this in the following way. I write this as the partial derivative with respect to y, because in the integral now y is a scalar. Why? Why is y a scalar? because of our choice of coordinate system. Right? We have chosen the coordinate system such that y points into the z direction. So therefore I know that if I now take the derivative with respect to y, it's the derivative with respect to the absolute value of y pointing in the direction of y. Okay, so now if I take nabla y of this expression here, sound will be back in a second. Okay, if I now take the gradient with respect to y of that expression, I need to take 3 contributions to that derivative into account. Right? The first part will be just the derivative of the 1 over y and the rest unchanged. So this gives me minus 1 over y squared integral 0 to y x squared dx f of x. Then, keeping the 1 over y fixed, I need to take the derivative of this integral with respect to y, which is a derivative of an integral with respect to its upper boundary. So it's just y squared f of y. So the y cancels, and I get plus y f of y from the second contribution to that according to the product rule. But then you see, sorry, this is a plus. Then you see now I have to take the derivative with respect to y of that here as well. That's now the derivative of an integral with respect to its lower boundary. So it's minus the integrand at the boundary. So it's minus y f of y. Well, how convenient, right? So you see, you can write this as minus 4 pi 1 over y squared times the unit vector in y direction. I will write this as y divided by y cubed, right, which is the same thing. And now integral from 0 to y x squared dx f of x. Okay, and now with that result, we can return to this expression there. Let me now put a minus sign into that because it has to be there and I lost it somewhere. So I'm writing minus this prefactor 2 pi, that prefactor 4 pi gives an 8 pi squared. Then all the rest, right? Alpha square divided by mu capital M. Then the Coulomb logarithm. Then this result rephrased in terms of velocities. Right, so y is now v capital M. So I have a factor v capital M divided by v capital M cubed. And now an integral from 0 to vm squared dvm f of vm. And that's the end of the story, right? Because unless we fix the distribution f of vm, we can't really move on. Suppose we insert for the velocity distribution of the small bodies a Maxwellian. Right? Then you have an integral of the type x squared dx Gaussian of x. If we only had an integral dx Gaussian of x to a finite boundary, we would get an error function. Now we have this prefactor of x squared in the integrand, or Vm square here. Nonetheless, you can translate this to an error function, and you see the result in the lecture notes. Okay, but let me do a different thing here. First of all, this at the end is Chandrasekhar's equation for dynamical friction. And remember the assumptions that we have made. One of the assumptions was that the distribution of small objects here is homogeneous in space. Right? We are assuming the same velocity distribution irrespective of where we are in space. We don't need to care for that because we have assumed that the spatial distribution of small objects extends to infinity anyway. Nonetheless, we need to take care of the Coulomb logarithm here, which, as you saw, is essentially a constraint on the maximum eccentricity that the hyperbolic relative orbits can have. It depends on the specific system that you have in mind what a reasonable number for this Coulomb logarithm could be. Right? Also, there are modifications of Chandrasekhar's formula where possible spatial inhomogeneity of the small objects is taken into account. Okay? All right, sometimes you see this formula written in a different way. For example, if lambda squared is much larger than 1, then this logarithm here is roughly the logarithm of lambda squared, or 2 times the logarithm of lambda. And then you see a factor of minus 16 pi squared out front here, and a lambda, ln lambda in here. But let me not go through these things. Let me discuss limiting cases. They are very instructive. First of all, let me write down the constants in a different way, alpha squared divided by mu m. So this is gmm squared divided by mu m, just because alpha was our coupling constant. So this is g square m square divided by m, capital M square, and multiplied with m plus m if I insert the reduced mass mu. Okay, so you see the m square cancels, one of the small m's cancels as well, and you see this is g square m plus m. And if capital M is much larger than m, you can just write g square mm. These are also simplifications that you often see. All right, but now with that, let me have a look at 2 limiting cases, namely, first limiting case, Vm small. What does this mean? Well, the velocity distribution f of v small m will have a certain shape. Right? It will define a certain velocity dispersion of the small objects. For example, suppose you have a Maxwellian here, will be characterized by a velocity dispersion, and what we are now going to study is cases where V capital M is very much smaller or very much larger than the velocity scale defined by the distribution f of Vm, V small m. So let me first say Vm is small in that sense. Then I integrate only over a small part of this velocity distribution. Then I can do the following thing. This integral will be approximately f of 0 times the integral of Vm squared dVm. So this is Vm cubed over 3. So this will be Vm cubed over 3 with capital M. And that's one approximation. If the mass, the large mass, is already rather slow compared to the velocity dispersion of the small objects, then we get this as an approximation, and the limiting case of this equation is, let me write it this way now, minus 16 pi square, then g square m, let me simply apply also the limit that capital M is much larger than small m. Good, now Vm divided by Vm cubed times Vm cubed divided by 3 f of 0. So then you see what happens is that the Vm cubed just drops out, and the change of the velocity V capital M, the change of the velocity of the big object, is just minus a constant times the velocity itself. What's the solution of this? The change is proportional to the quantity itself, right? It must be an exponential. So then, if the object is already very slow, then its velocity decays exponentially. Once it's slow enough, you bring it to a halt. Right? Once it's slow enough, then the dynamical friction is very strong. So this cancels out. And we have d ln Vm with respect to dt equals constant. Right? This beautiful constant. So the constant that remains must have the dimension 1 over time. It must be a characteristic, must set a characteristic time scale for the orbit to decay, or the velocity to decay. Does it have the unit, the right units for that? Well, check it, okay? It does. So these constants just set a time scale 1 over tau, let's say, and then you get an exponential of initial velocity V capital M times e to the minus t over tau. Okay, other limiting case, Vm large. And again, this means large compared to the scale that f, the velocity distribution for this, V small m's, that this distribution sets. So then I can approximate 0 to Vm, Vm squared dVm f of Vm by an integral to infinity. But this is now an integral over the complete velocity space, over the velocity distribution. There's a spatial number density, almost, right? Because what is missing for the volume integral is a factor of 4 pi. So this will be n, the spatial number density of small objects divided by 4 pi. Okay, but if this is the case, then we can write dVm divided by dt is minus 16 pi square g square capital M. Oh, sorry, I forgot the ln lambda here. Okay, capital M. There's a small m as well. But together with this number density, that's going to be the mass density of small objects. Right, so I write rho, then we have to divide by 4 pi, then the equation simplifies to that. And what remains is now Vm divided by Vm cubed. Okay? So first of all, you see, then the dynamical friction effect of the small masses does not depend on the small mass anymore, but just on the number, on the mass density of these things. Yeah. Yes. Well, suppose you have a galaxy moving through a collection of dark matter particles. Right? Then you have an enormous number of orders of magnitude between the two. Depends on the situation. Right? Okay. Again, ln lambda. All right, but now you see, now the friction is proportional to 1 over velocity squared. So now you have Vm dot proportional to Vm to the minus 2. Now what's the solution of that? So now you see, this means that Vm cubed dot times 1/3, if you wish, must be a constant. And it's going to be a negative constant. So now you can integrate both sides, and you see that Vm cubed is then proportional to 1 over time, constant divided by time. 1 over time because it's a negative constant, right? All right, so this means that here Vm will be proportional to 1 over the cube root of time. This is going to be very slow. In other words, initially when the velocity of the large mass is large, compared to the velocity scale set for the small objects, then dynamical friction will be very inefficient, right? And the orbit and the velocity of capital M will change only very, very mildly with time. Later on, when the velocity is already small, it will decay exponentially. So the velocity will go like this, right? If you suppose you have a mass distribution of small objects, and you send a big object into it, let's say here, the velocity initially will almost not change. Once it leaves the object, it will not change at all. Let's exaggerate a little bit. We'll do something like this, right? Will at first almost not change, and at the end change very quickly. So it will be a spiral that will become steeper and steeper, right, like this. Okay? Good. Now time is almost up, unfortunately. And this means what does this mean? Let me very briefly sketch the idea behind Fokker-Planck. The idea is very simple, in fact. All right, but keep in mind, in this effect of dynamical friction, right, what is the main point? We have completely non-dissipative dynamics, yet we have a friction effect. The friction comes about because deflected objects collect in the wake behind the deflecting object, and by their enhanced gravity slow it down. You have calculated the effect. You have seen the limitations of that calculation. Right? They were idealizing assumptions. First of all, we assumed that there is a maximum eccentricity of the hyperbolic orbits that we can deflect. We have assumed that the small deflected masses have a spatially homogeneous distribution. All of these assumptions need to be revisited. The importance is the existence of that effect, and then you can look up the literature for modifications of that of this calculation. All right. Now, very briefly, Fokker-Planck. What's the main idea? That would have been number 2 for today. Fokker-Planck. Very, very frequently used because the approach is very general. The idea is the following. So far we have assumed that the total time derivative of any phase-based distribution is 0. You can assume that as long as dynamics is Hamiltonian. Right? Then necessarily phase-based volume covered by a system is unchanged and df dt is 0. So this does not need to be the case if we have interactions between particles that are non-Hamiltonian, for example, direct collisions. So then, at the point in phase space where we consider f, we will have a contribution that I can write as gain minus loss, right? I will gain some particles there and I will lose some particles there. I will describe the gain and the loss by a transition probability. Transition probability from one point in phase space to another. Let me write with W the phase space position, and then say I will just assume I have a transition probability from one point in phase space W by an amount by an amount delta W. So for example, right, I'm at position xp in phase space, a collision encounters, or a collision occurs. Perhaps x does not change, but the momentum will change. Right? Okay, so that's a transition probability. So then I can quantify the gain term and the loss term. Then I can write the gain is an integral that tells me with what probability do I collect how many particles from somewhere else at the position where I am. Right? So how much contributions do I get at my position in phase space from scattering events all around the place? So what is this? Well, first of all, I will have to integrate over all possible changes of phase space coordinates. The number of particles that are there times the transition probability from there by an amount delta omega. Right, so that's the transition probability from somewhere else times the number of particles that are somewhere else relative to my point in phase space. That's the gain term. The loss term is simpler. That's just the number density of particles here times the transition probability to somewhere else from here. Okay, now the idea of Fokker-Planck is just to make a Taylor expansion here and say, okay, I will assume that any collision will change the phase space coordinate only by a small amount. So the essential idea is now to say this thing here, the integrand in the gain term, is approximately the same expression at phase space position W. Now minus dW, let me just write f psi at these arguments times delta W plus 1/2 d2W f psi delta W squared. We make a second order Taylor expansion of the functions in the gain term. That's all of the essential idea. And then you see, if you now compare the gain and the loss terms, and you insert this second order Taylor expansion up here, and you subtract the loss term, then only the constant is gone, and the rest remains. So then gain minus loss will be this expression here. Okay, but now we are carrying out an integral over delta W. The f does not depend on delta W anymore, because the f will only be evaluated at the phase space position W and nowhere else. So this means that I can separate here the f from the psi and write minus dW f d1 times, f times d1, f times an expression d1 that we have to specify, plus dW squared of f times d2. And d1 and d2 are called the Fokker-Planck diffusion coefficients. What do they look like? See, since I can separate the W's differentiation here and the f from the delta W integral, you can write d1 is an integral over dW, an integral over delta W, psi of W and delta W times delta W. So what is this? This is the transition probability by collisions or whatever for getting away into any other point starting from position W in phase space. So that's the complete transition probability from point W in phase space times delta W. So it's the mean change of phase space position delta omega. Okay. Number two is this expression here, right? That's not the mean, but the variance of the change in phase space coordinate. So, and this means that in the Fokker-Planck approximation, you see an evolution equation for the phase-space density, which looks like this. Right, and this is what I wanted to show you. I wanted to go a little bit further and apply this to actual distributions and so on. But you see, it's our first encounter at the end of the lecture, well, very soon. 1 second. Our first encounter with collision terms. We are taking these collision terms into account by postulating a transition probability from one point in phase space by a certain amount. That's the psi. Then we Fourier expand the gain term. Sorry, we Taylor expand the gain term, subtract the loss term. We do this to second order and acquire these two Fokker-Planck diffusion coefficients, D1 and D2. And once you know the collision process, you can evaluate these diffusion coefficients. And it also turns out that D1 and D2 are dependent on each other. And so you can write D1 as a function of D2. Yes? It's in fact a second moment, yes. The mean is this. If you subtract the mean, then you can calculate it. That's correct, yes. Okay. Yeah. Not easily. Not easily, because we are modeling the gain and loss terms here as being proportional to the existing phase space density. Right? So if you want to model changes in stellar populations in this way, you need to assume that gain and loss in these populations are proportional to what is already there. This may or may not be the case. Right? So for example, the probability for a star to die is usually quite independent of other stars in the neighborhood. So therefore, in this context, I would be careful about this. Yeah. One more thing. Suppose you have to do with bosons. Well, why not? Right? Any photon is a boson. If you want to apply the Fokker-Planck equation to bosons, there's a very interesting effect, right? Because where there is one boson, there likes to be another, right? Because of Bose statistics. So in the case of Bose statistics, you do not have a factor of f here, but a factor of f times 1 plus f, which takes into account that where you have a boson, another one likes to be. Okay? Now, f and f times 1 plus f are only different if f is comparable to 1. Right? So if you have a dilute distribution, Bose statistics doesn't matter. But you may have situations where Bose statistics is in fact important. And then in the Fokker-Planck equation, this term is no longer linear in f, but quadratic essentially. All right? And you see this in the so-called components equation that is the Fokker-Planck equation for bosons. All right. We could go on for quite a while, right? But now the lecture is over, at least as far as new content is concerned. So as announced on Monday, I'm going to be here on next Monday to summarize the lecture and answer your questions if you have any. On Wednesday, Christian Angrig is going to come and he will go through the problems and he'll discuss the problems with you and what the purpose of the problems was and so on. All right, so thank you very much for today and maybe we see each other next Monday. Oh, yeah. No, it's late enough. I'll say this on Monday. All right, see you then.